Hello, I am the mild Mr. Dayhawk, and today I am going to prove to you that the derivative of sine is cosine and the derivative of e to the x is e to the x. So, first of all, if y equals sine of x, then dy by dx is equal to cosine of x. The question here is, why? And what is the proof? So, for this proof, we're going to need a couple of facts. First one is that for small values of theta, so for theta significantly less than 1, in fact, we want to do the magnitude of theta significantly less than 1, so numbers around 0.2, 0.3, sine of x, sine of theta, let's be clear, is approximately theta. And cosine of theta is approximately 1 minus theta squared over 2. Now, this gives us some actually very valuable things, because as these become more and more accurate as theta tends to 0, we can actually rearrange it, and we can see that sine theta over theta is approximately 1. And again, this gets perfectly accurate as we tend towards 0, so we can in fact say the limit as theta tends to 0 is equal to of sine theta over theta is exactly 1. Further, rearranging the cosine, we have that cosine of theta subtract 1 all over theta is going to be approximately equal to negative theta over 2. But again, this becomes more and more accurate as theta tends to 0, which means we can say that the limit as theta tends to 0 of cosine theta minus 1 over theta is exactly equal to, well, we've let theta tends to 0, so this is negative 0 over 2, which is in fact just 0. And these two facts are going to be absolutely vital in our proof. This one and this one. Okay, and now to prove our derivative, we just need to remember our rule of derivative, our differentiation formula from first principles. If y equals f of x, then dy by dx is going to be equal to f of x minus h. Ooh, forgot the limit in front there. The limit as h tends to 0 of f of x plus h minus f of x all over h. And in this case, we're dealing with y equals sine of x. And so our dy by dx is going to be equal to the limit as h tends to 0 of sine of x plus h minus sine of x all over h. Now, you might ask yourself, what do I do here? Well, the trick is to notice that this has an addition inside the sign, and so we're going to use our sine addition formula. Sine of a plus b is equal to sine a cosine b plus sine b cosine a. And so applying that here, we get that this is equal to the limit as h tends to 0 of sine, our a is x, cosine h plus sine h cosine x, still minus sine of x, and all divided by that h. And now what I'm going to do is I'm going to group them together. What I want is these sines x, this sine x and this sine x, to be together. And so I'm going to write this as the limit as h tends to 0 of sine x cosine h minus sine x all over h, and then split this into another fraction plus just the other part, which is sine of h cosine x all over h. But let's split the limit as well, because limits are linear so long as the limit exists. And so we end up with this. Now, there's a little bit of factorising we can do here. There's a sine x here and a sine x here. And equally, that will leave us with just h's there. So we'll do the same here. And I'm going to write this as the limit as h tends to 0 of sine of x cosine, put that in black, cosine h minus, if I factor out the sine of h here, then that's going to be 1 all over h. And then we're still adding on the limit as h tends to 0 of, let's take that cosine x out, so we're just left with h's over here, of sine of h over h. And now, notice these blue terms actually don't involve h at all. So because they don't involve h at all, we can actually take them entirely out of the limit. And so we're left with sine of x, and of course this is all equal to our original derivative, multiplied by the limit as h tends to 0 of cosine of h minus 1 over h plus cosine of x times by the limit as h tends to 0 of sine of h over h. But these two things are exactly the two things that we defined at the start, and they're equal to 0 and 1 respectively. So this is equal to sine of x times by 0 plus cosine of x multiplied by 1. And this is our proof, because the simplification of that is just sine of x times 0 is 0, plus cosine times 1 is cosine. That is just cosine of x. And that is our derivative, because remember where we started with was dy by dx is equal to this, and then we just rearranged that until we got to cosine of x. We didn't do anything to both sides of the equation at all, we just manipulated the algebra until we got cosine of x, and therefore dy by dx. So if y equals sine of x, let's be sure we start where we need to be, then dy by dx equals cosine of x. And that there is our proof. Okay, so that's the proof that sine of x differentiates to cosine of x. Now let's have a look at e to the x. We want to prove that if y equals e to the x, then dy by dx equals e to the x. And for this one, we're just going to need one fact, and that is the definition of what the number e is. The number e, which is approximately 2.7, is defined precisely this way. E is defined to be the limit as n tends to infinity of 1 plus 1 over n to the power of n. And you can try this out and plug it into your calculator. Just pick n as a really, really big number, and you'll see that it tends towards our value of e that we're looking for. So we're going to use this as our definition, and of course just the definition of derivative. So we are saying that dy by dx is equal to e to the x plus h minus e to the x all over h. And now the obvious thing to do, hopefully we can see here, is that this is a power, and so we can just split the power into a multiple, and we end up with this being equal to exactly I forgot the line limit there, that's kind of important. The limit as h tends to 0, let's not forget that, and we end up with this being equal to the limit as h tends to 0 of e to the x multiplied by e to h, just our power laws there, minus e to the x over h, and then hopefully we can see exactly as last time, we've got e to the x here and e to the x here, we can factor those out and we're left with the limit as h tends to 0 of e to the x times by e to the h minus 1 all over h. And then factor that out of the limit entirely, and we get that it is equal to e to the x multiplied by the limit as h tends to 0 of e to the h minus 1 all over h. And now we're done, provided this bit here is equal to 1. So if the bit in blue is exactly 1, then our proof is done. So this is where we need to bring in the definition of what E is. That E there, remember that E is going to be equal to the limit as n tends to infinity. Be careful, my h's and my n's don't look exactly the same. As n tends to infinity of 1 minus, 1 plus even, 1 over n, or to the power of n. Now this seems fine, this seems like it's going to be great because we've got two limits here, but notice that our limits here and our limit here are not the same. One is h tending to 0, one is n tending to infinity. So what we really want to do is pick our n in such a way, pick our n in such a way to find it to be something that as n tends to infinity, the thing we're going to call n tends to 0, effectively. Or the thing we're going to relate it to tends to 0. We're going to want to turn it in terms of h. So to do this, the trick is to say that n is equal to 1 over h. And as that tends to infinity, h will tend to 0. Or in fact the other way around, as h tends to 0, 1 over h tends to infinity. And this gives us the power we need to solve this problem and prove that it is indeed 1. Okay, so carrying back on, we've said that n is 1 over h, so this here, this limit over here, is now e is equal to the limit as n tends to infinity, but remember that's n tending to infinity is the same as h tending to 0 of 1 plus 1 over h, all to the power of 1 over h. But our rules of fractions tell us that 1 over h is just h, and so that's the limit as h tends to 0 of 1 plus h to the power of 1 over h. Which is great now because we've got a limit as h tends to 0, which means that we can just combine it with this limit. And so what we're left with is, this is equal to e to the x, the bit we care about, multiplied by the limit as h tends to 0 of 1 plus h to the power of 1 over h, that's our e, that's the definition of e right there, all to the power of h minus 1 over h. And now, the key thing here is this power to the power. That's going to become something just going to simplify to multiplying them. And so this is going to be equal to the limit as h tends to 0 of 1 plus h to the power of h over h minus 1 all over h. And h over h is 1, and so this is equal to e to the x multiplied by our limit as h tends to 0 of 1 plus h minus 1 over h, which is equal to e to the x times by the limit as h tends to 0 of 1 plus h minus 1 is just h over h, which is in fact absolutely just 1, which is equal to e to the x. And there is our proof, our final part of our proof, that if y equals e to the x, then dy by dx is also equal to e to the x. Okay, thank you very much for watching, and I'll see you in the next video.